Today I want to talk a little bit about the combined gas law and introduce Avogadro's law with respect to gases. We've heard of Amadeo Avogadro before because of Avogadro's number, which is equal to 1 mole, 6.02 times 10 to the 23rd. But this is in the context of gases, which is still related to moles, and we'll get into that. But first I want to combine together all of the gas laws. If you've seen some of my other videos, you've seen that I have one on Boyle's law, Charles' law, and Gay-Lussac's law. When you combine all of those together, you get the aptly named combined gas law. Combined gas law is not one of my favorites personally, because I feel like it's just a whole bunch of algebra, and I think it's harder to predict what's going to happen because you have so many variables in there. So the combined gas law is really putting together Boyle's law, which is the V1 P1 equals V2 P2, Charles' law, which is V1 over T1 is equal to V2 over T2, and Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So we put all those together, and this combination of variables gives you the combined gas law. So what that really says then, if you're thinking about the individual laws, is if you hold the other variable constant, so if my temperature doesn't change, for example, so I keep the temperature the same, then this would just divide out, and I'd be left with Boyle's law, right? So if I keep one of the variables, pressure, as constant, then that'll divide out, and then I'm left with Charles' law. If I keep volume constant, then I'm left with Gay-Lussac's law. So you can actually kind of back out all of the individual relationships from this, but I personally prefer to start with the individual relationships because I think those are more intuitive. I think that kind of binary relationship between two variables is easier to understand and predict the outcome of than to see a whole big problem like this. So for example, I might have a problem that looks like this. So I have an ideal gas. It has an initial volume, an initial temperature, and an initial pressure. And it wants to know what the volume is if I lower the temperature and lower the pressure. So again, the reason I don't like this, which I know it's kind of silly to do a video about, and here's all the reasons I don't like this, but that's what I'm doing. Is that you're given so many things and there's so many things changing that it's hard to tell exactly what's going on here. It's hard to predict what we think the outcome is going to be, and we rely too heavily then on our calculators. Let me show you what I mean. So let's list out the variables that we're given. So we have an initial volume. That's 5.20 liters. We're looking for the final volume. That's what it's asking for. So my V2 is going to be my variable that I'm solving for. My initial temperature here is 27 or 22.7 degrees Celsius, which I'm going to convert to Kelvin, right? So 22.7 plus my 273.15 gives me 295.9 Kelvin. And I'm just going to do the conversion there because I trust at this point you guys are feeling pretty snappy about temperature conversions. And then my 15.0 degrees Celsius, I'm going to convert to Kelvin as well. So I'm lowering it, so I'm expecting that to be smaller. So that's going to give me 275.2 Kelvin. And then I'm given an initial pressure and a final pressure. So my initial pressure is in kilopascals, it's 335. And because I'm given the same unit for pressure, I'm just going to keep them that way. I don't have to convert anything. If I was given different pressure units, or if I had to factor, if it asked for something different, then, but because I'm given the same, the units will just divide out. Okay, so if we kind of take each piece of this, we're looking for how the volume changes with a changing temperature and a changing pressure. Now, if I was to rearrange my equation, because that's what I like to do, is to rearrange and solve for the variable I'm looking for. So I'm going to rearrange this thing and solve for V2. Then I end up with V2 is equal to V1 P1 T2 divided by T1 P2. Right, so I kind of cross multiplied, divided this out, and then I ended up with solving for my V2. Now again, this is part of the reason I don't like this is it's just a lot of variables. So we're throwing all these variables in there, you're given all these numbers, and then you alphabet soup them into your calculator and then it spits out a number. I like for problem solving, when you have a problem that you can plug in and kind of figure out what you think is going to happen. But for this one, we're changing two things. We're changing the temperature and we're changing the pressure. When the temperature goes down, we would expect the volume of the gas to go down, right? Because that's our direct relationship. When I cool things off, then that's going to slow down the motion of the particles. That means that the gases molecules will get closer together, so the volume decreases. Now, if we think about pressure, though, there's an inverse relationship between pressure and volume. So my pressure is going down here, which means my volume is going to go up, right? So I decrease my pressure, increase my volume. So there's that relationship there too. So without really knowing kind of more about the system, more about the conditions, more about the gases, it's hard to predict how this is going to change it, because they're both changing it in opposite directions. One of them is pushing this down, the other one is pushing it up. So I think that that's kind of a challenging piece to this, is I like being able to predict things. I don't like just plugging things into my calculator and solving. But that's what we're doing, and that's what combined gas law is all about. So when I plug in my values here, and again, I'm just going to kind of give you, I'm assuming you can plug these in and feel pretty comfortable with the algebra here. It's going to spit out an answer in liters, because I'm going to have liters, kilopascals, Kelvin, and then Kelvin kilopascals here. So my units will divide out for my temperature and pressure. It'll leave me an answer in liters. If I'm looking at sig figs, it looks like I'm going to be limited to 3, and I end up with a volume of 6.17 liters. Which again, if I was looking at this problem, I wouldn't have necessarily been able to predict that the volume was going to go up, because the temperature goes down. So yeah. I've given you my spiel. I will get off my soapbox now. This is just a good example of combined gas law. It combines together all these kind of binary laws. So there you go. Speaking of binary laws, Amadeo Avogadro also studied gases. So what he was studying were particles, numbers of particles, which is why the mole is named Avogadro's number. And he was around in the late 1700s, early 1800s, so kind of around the same time frame as Gay-Lussac and Jacques Charles, a little bit after Robert Boyle in terms of gas law kind of fame. So Amadeo Avogadro is an Italian scientist. Again, I usually claim him as a chemist. You could probably call him a physicist as well. He wasn't very well known or respected in his time, but a lot of his studies were found to be true afterwards. It's hard to get your head around things like numbers of particles. And what he ended up saying, and this is Avogadro's law, is that equal volumes of gases, if I have a constant pressure and temperature, have an equal number of particles. So equal volumes have an equal number of particles. And so what he could say is, regardless of the identity of the gas, 1 mole of that gas is always going to have the same volume at STP. STP here is standard temperature and pressure. STP. So standard temperature and pressure for gases is 0 degrees Celsius, or 273.15 Kelvin, and 1 atmosphere of pressure. And then, of course, you can do the conversions there too, kind of depending on the pressure units that you're looking at. But standard temperature and pressure, 0 degrees Celsius, 1 atmosphere of pressure. And 1 atmosphere is kind of what you're sitting at sea level on Earth. So anything other than that is not going to be a standard temperature and pressure, which you have to factor in when we're thinking about gases. So the molar gas volume, which is sometimes abbreviated with the symbol V sub m, is referring to the volume of 1 mole of the gas. So 6.02 times 10 to the 23rd particles of that gas, whether it's individual atoms or molecules, is going to have a volume of 22.4 liters. Again, regardless of the identity, which is kind of wacky. So what shakes out of this, what Avogadro's law is sometimes written as, is a relationship, a direct relationship between the number of particles and the volume. So it's really looking at kind of, if we think about number of particles as n and the volume is v, then we look at how the volume changes with a changing number of particles. So as I increase my n, then my volume will go up. It's a direct relationship. They're directly proportional. Now really, Avogadro's law is that equal volumes of gases have equal number of particles. But if we're thinking about this from a mathematical standpoint, then we can talk about the ratio because of this direct proportionality. So long as we are keeping constant pressure and temperature, then we can say that regardless of the conditions, whatever temperature and pressure we're at, if we're at non-standard conditions, then we can still figure out what the volumes are going to be and how they're going to change. And that ratio of volume over number of particles is going to equal some number. And if I change it, then that's going to give me that same ratio. That's that direct proportionality. So that means that I can set these guys equal to each other. And sometimes we see that Avogadro's law is written symbolically this way, which just shows that direct proportionality between a changing number of moles of gas and a changing volume, which again feels pretty intuitive because if I'm blowing up a balloon, so let's say that I'm having a party in non-COVID times and I'm blowing up a balloon, I'm exhaling carbon dioxide into the balloon and the balloon gets bigger, right? That's really all there is to it. More stuff gives me more volume, which again feels pretty intuitive, but that's the way that we can we tell you by how much the volume goes up with the changing number of moles. But the key to it is that equal volumes of gases have an equal number of particles, so long as we keep these pressure and temperature variables constant. So that's combined gas law and Avogadro's law. And in some follow-up videos, now we're going to put all of those together. We're going to add in Avogadro's law to the combined gas law to give you the ideal gas law. And we'll talk more about that later.